Good morning, dear students, and once again, welcome back to our course. In the last lecture, we discussed in detail about the concept of fundamental aspect related to signal flow graph, and we also discussed what exactly Mason's gain formula is. So, as far as history of signal flow graph is concerned, the concept of SFG was first of all invented by Professor C. Shannon, and how signal flow graph is used to find out the parametric function of the system was introduced by Professor C.J. Mason, and he proposed a formula to calculate the transfer function of a system if the system is represented in the form of signal flow graph. That formula is called as Mason's gain formula. So in the last lecture, we discussed in detail about what exactly Mason's gain formula is and how we can derive the parametric function, which is also called as transfer function of a system, if the representation of system is available in the form of signal flow graph. So ultimately, we are having with us this mathematical equation like C of s by R of s, where C of s indicate the Laplace transform of output, R of s indicate the Laplace transform of input. So the ratio of C of s by R of s indicate the transfer function, and on the right hand side we are having summation I vary from 1 to n, which is nothing but pi delta I divided by delta. So what is p, what is delta, what is n? These parameters we discussed in detail in the last lecture, where this n indicate the number of forward path, p indicate the gain of forward path, okay. So this n indicate the number of forward path, this p indicate the gain of forward path, and this delta indicate system determinant. System determinant. That is important. And then we discussed in detail about how to find out the value of p, how to find out the value of n, then what is the concept of pi, what is the concept of delta. In detail, we had a discussion on this aspect. So to calculate the value of delta, the thing is that first of all we need to identify that how many number of loops are present in the system. It may be self loop, it may be non self loop, but the thing is that we need to find out that how many number of loops are there, say L1, L2, L3, and so on. And then we need to find out their corresponding gain. So I told you that in order to find the value of gain, maybe for forward path, maybe for any loop, the thing is that we need to multiply the gain of branches which are responsible for the formation of that particular forward path or that loop. Then we need to identify that how many number of uh, loops are touching, how many number of loops are non-touching, and so on. And once we have the idea about all these parameters, then it is very easy for us to find out its corresponding transfer function if we know these details or these minute details about the system. Then in order to calculate the value of delta I, again we need to use the same formula which we have used to calculate the value of delta. The thing is that whatever the loops or the individual loops or the summation of gain product of two non-touching loop or three non-touching loop, these loops are not in physical contact with that particular forward path. For example, if we are calculating the value of delta 1, then in that case we need to take only those loops which are not having any node which is in common with your first forward path. That is very important. In the same way, that same logic we need to apply in order to calculate the value of delta 2. That means to calculate the value of delta 2, whatever the loops which we have identified in the system, only those loops which we need to take to calculate the value of delta 2, which are not in physical contact with your second forward path. That means they do not have any common node between your second forward path and any corresponding loop. It may be individual non-touching loop, it may be a pair of two or three or four non-touching loops. If you apply that logic, then it is very easy for us to find out the transfer function for any system if its signal flow graph is available with us. And then we discussed how to find out the transfer function of a system if its signal flow graph is known to us. So there are some 4 to 5 steps that we need to implement. The first step is we need to identify that how many number of forward paths are available in the system. That means we need to calculate the value of n. That is very important. And then in step number 2, we need to calculate the gain of those forward paths. For example, in the previous case, suppose we considered that the number of forward paths are nothing but 2. Now we need to calculate the value of P1 and P2, where P1 indicate the gain of first forward path, P2 indicate the gain of second forward path. Then in step number 3, we need to identify that how many number of loops are there, and we need to calculate the loop gain of each loop, say L1, L2, and so on. Then we need to determine the system determinant, followed by delta 1, delta 2, and so on. And once we have all these informations, like what is the value of n, what is the value of p1, p2, followed by l1, l2, delta, delta 1, delta 2, then it is very easy for us to apply Mason's gain formula in order to find out the transfer function of the system. Because from this equation, it is very clear that in order to find the value of transfer function, we should know the value of n, which indicate number of forward path. We should know the value of p1, p2 corresponding to first and second forward path. We should know the value of delta 1, delta 2, and we should know the value of delta. So all these things we are going to calculate from equation or from step number 1 to step number 4. So once we have the information about all these parameters, then the thing is that we need to put and club all those sub parameters, put them in equation number 1. Suppose this is your equation number 1. We can easily find out the value of what? Transfer function. And this formula is called as Mason's gain formula. That is important. Mason's gain formula. That is important. And then we, in the last lecture, we also solve a numerical, where the objective is we have the graphical representation of the system in the form of signal flow graph, and our objective is to find its corresponding transfer function using Mason's gain formula. So in this numerical, we came to know that here we have number of forward paths as 2, and then we calculate the value of P1 and P2, and then we identify that in this case total number of loops are nothing but 5. Then we have calculated the loop gain for each loop, and then we calculated the value of delta followed by delta 1 and delta 2. And once we know the value of all these parameters, then it is very easy for us to find out its corresponding transfer function. So we apply those steps one by one. In first step, we have identified that how many number of loops are there, and is going to be 2. Then we need to reduce the generalized formula. This indicate your generalized formula, and we have converted that into the specific formula like this: p1 delta 1 plus p2 delta 2 divided by delta. That is important. And then step number 2, calculation for forward path gain. So here we have identified that total number of forward paths are 2. That's why p1 and p2. P1 is A B C D E, P2 is AB into GE. And then in step number 3, we need to identify that how many number of loop gains are there. And then individual loops are 5. We have calculated first their path, their nodes, which are corresponding for the formation of those loop. And then we calculated their loop gain individually. So L1, L2, L3 up to L5. And once we have knowledge about how many number of loops are there, how many number of our paths are there, then it is very easy for us to apply step number 4 to find out the system determinant, like delta, delta 1, delta 2. So once we calculate the value of delta followed by delta 1 and delta 2, then it is easy for us to club all the information, put them into Mason's gain formula to find out the corresponding transfer function of the system. So this is what our final output equation is. Now, in today's class, again we are going to solve some numerical on Mason's gain formula. That means if you know the signal flow graph representation of a system, how to find its corresponding transfer function using Mason's gain formula. And this will be the last lecture on signal flow graph. In the next lecture onwards, we are going to learn another aspect where we are having the representation of system in the form of block diagram, and how to apply block diagram reduction technique to find out its corresponding transfer function. That we are going to learn from next lecture onwards. But now in this particular session, let us focus on solving some more numerical on Mason's gain formula. So this was numerical number 2 on the topic signal flow graph, where our objective is to find the transfer function of the system using Mason's gain formula. So I want everyone to please draw this structure, and let us try to apply the logic of Mason's gain formula to find out its corresponding transfer function. Though the structure is quite complicated, but it is very easy for us to identify first how many number of forward paths are there. As I told you that in order to apply the value of, or in order to apply that Mason's gain formula, we need to apply some steps. So in step number 1, what we need to do, we have to calculate the value of n, where n indicate number of forward paths. So calculate n, how many number of n's are there. How to identify n? It's very easy. Started with input node. Suppose this is nothing but your input node. Why it is called as input node? Because it has only outgoing branches. And this is going to be your output node. Why it is called as output node? Because it has only incoming branches. So if you start from input node, move towards the output node, keeping the sense or keeping or maintaining the sense of flow of signal in a specific branch, then those paths are nothing but your forward path. For example, if you start from node number 1, then you move to node number 2 like this. And then at node number 2, you are having many paths. Let us try to identify that what are the possible paths. We are not in a position to move from node number 2 to node number 4. Why? Because the flow of signal is from 4 to 2, but we want to move from 2 to 4. So this is not the valid path. In the same way, we are not in a position to move from node number 2 to node number 3 like this. Why? Because the flow of signal is from 3 to 2, but we want to move in the direction from 2 to 3. So this will not be the valid path. In the same way, we are not in a position to move from node number 2 to node number 5, because the flow of signal is in 5 to 2, but we want to move from 2 to 5. So this will not be the valid path. So out of these 4, 3 are invalid. So but obviously we have only one valid forward path, and that is from node number 2 to node number 3 via branch of gain G2. So this will be the second branch. And then at node number 3, again we need to check how many number of paths are there, or how many number of branches are there through which we can reach to our final destination, which is nothing but the output node. So at node number 3, again we need to check. So see, we can move from 3 to 4 via this particular path. Yes, we can move. Why? Because the flow of signal is from 3 to 4, and we want to move again in the same direction. So this will be the next path. In the same way, we may have the possibility like we can move from 3 directly to 5. Yes, this is also possible. Why? Because the flow of signal is from 3 to 5 and we want to move from 3 to 5. So this can be the second possible way. But let us try to first focus on the straight line, and then we will identify that apart from this, what will be the possible way to reach from input to output node. And then from 4 to 5, again we have one path of gain G4. We cannot select this particular path because while calculating the value of forward path, we need to take only one node at a time. No node can be repeated twice. So here we have only one gain, that is important. And then from point number 5 or node number 5 to node number 6, again we need to move through a branch of gain exactly equals to 1. So this will be the first forward path, having a gain of G1 multiplied by G2 multiplied by G3 multiplied by G4. That is important. In the same way, if you move from point number 3 to point number 5 directly through gain of G8 and then multiplied by this 1, it will be the second forward path. So I think in this particular numerical, we are having total two forward paths. First one is a gain. Suppose if you are interested to find out the gain of forward path P1, so it will be like G1, G2, G3, and G4. In the same way, if you are interested to find the gain for second forward path, say P2, so it will be like G1, G2, then we need to take G8. That's it. So this is what the way we can identify that how many number of forward paths are there in the given structure. I hope this point is clear to everyone. I want everybody to please note down these points because these points plays an important role to determine the transfer function of the system using Mason's gain formula. Once you have done with this, then let us try to identify that how many number of loops are there, and then identify that out of those loops, how many number of non-touching loop, pair of two non-touching loop, three non-touching loop, self loop, that you need to identify. Okay, I hope everyone is done with this particular portion. The thing is that you have to draw this structure. You have to find out how many number of forward paths are there. That means what will be the value of n, and corresponding to the value of n, we need to find out the specific formula to calculate the transfer function for this particular system. So n is 2, that's why we need to vary the value of I from 1 to 2 with a step of 1. So summation I vary from 1 to 2, pi delta I divided by delta. So that formula will be like p1 delta 1 plus p2 delta 2 divided by delta. That is important. So the same thing is mentioned over here. See, n is going to be 2. That's why the formula is reduced to equation number 1, p1 delta 1 plus p2 delta 2 divided by delta. So everybody please follow these steps. This is very important. And you have to note down this point simultaneously in your regular class book. In step number 2, we need to calculate the gain of forward paths. So here we have identified that there are two forward paths. First will be G1, G2, G3, G5, and second will be your G1, G2, and G8. So G1, G2, and G8 will be like this: G1, G2, and then directly from G8 2 like this. And first forward path is like G1, G2, G3, G4 like this. So this will be the first forward path and this will be the second forward path. Please note down these points. Once you have done with this, then in step number 3, what we need to do, we need to calculate how many number of loop gains or how many number of loops are there, and then we need to find out their corresponding loop gain. So how to find out that? Again, apply the same logic. Let us try to find out that how many number of loops are there in this particular system. So first try to identify that how many number of loops are there. So in this case, let us try to identify that number of loops. So I think this will be the first loop, or this will be the one loop which is available in the structure, starting with node number 2. Then we need to move to node number 3 and then coming back to node number 2 like this. This will be the first loop 1. Then we have another loop like starting with node number 3, then node number 4, then node number 5, then back to node number 3 is not possible because we are violating the flow of signal through branch this. So we can do one thing like yeah, you can start from node number 2, then move to node number 3, then node number 4, node number 5, and then we need to come back to through this particular path. So I think this will be the second loop. So 2, 3, 4, 5, and then coming back to 2. This will be the second loop. Let me write the nodes which are responsible for the formation of this particular loop. So starting with 2, then we have 3, then we have 4, then we have 5, 2, 3, 4, 5, and then coming back to 2. That is important. In the same way, we are having one more loop from node number 2, then node number 3, node number 4, and then coming back to node number 2 via this particular branch of gain G5. So it will be like 2, then 3, then 4, and then coming back to 2. That is important. Then we have one more self loop like this. So this will be a third loop, and this will be the fourth loop. Started with node number 4, ended with node number 4 with a branch of gain exactly equals to G6. That is important. Apart from this, let us try to identify, is there any possibility to form a loop in the structure? There will be one more possibility. See how many number of loops we have considered over here. First is the first loop is in between 2, 3, 4, and then 2. See, 2, 3, 4, 2, 2, 3, 4, and then 2 that we have taken. Then 2, 3, 2. 2 3 2 that we have again taken. Then 4 4, this will be the self loop that we have again considered. Then loop number 4 is 2 3 5 2 2 3 and directly 5. Yeah, this portion is we have not considered. So starting with node number 2, then we are moving to node number 3, and then from node number 3 to directly node number 5, and then from node number 5 following this particular branch we are reaching to node number 2. So this is missing. So 2 3 5 2, this will be the fifth node. So in this case we have total 5 individual loops that are available in this particular structure. So in step number 3, we need to find out that how many number of individual loops are there, and we apply the logic. The thing is that we need to start with one particular node, end with the same node, and while ending, it may possible that we may take one or more than one node in the path, or it may possible that no node is going to be take care in that particular loop formation, like self loop, like in this case loop number 4, or you can say with respect to this particular structure loop number 3 started with node number 4, ended at node number 4 without taking care of any other node in the path. So this will be your self loop, while the remaining 4 loops are non self loop. That is important. So once we identify that how many number of loops are there, now what we need to do, we need to find out their loop gain. So let us try to find out the loop gain for these loops. Now you tell me what will be the gain for first loop. That is important. So which one will be the first loop? It is formed between 2 3 4 2. See, 2 3 4 and then coming back to 2. So what will be the gain for this? It will be like G2 multiplied by G3 multiplied by G5. That's it. Because what is loop gain? It is simply the product of gain of branches which are responsible for the formation of that particular loop. That is important. So in this case, if you start from node number 2, you can move to node number 3 with a branch of gain G2. Then from 3 to 4, branch of gain G3, and then 4 to 2, branch of gain G5. That's why we need to multiply these three branch gain simultaneously, G2, G3 and G5. In the same way, if you take 2 3 2, what will be the gain for this particular loop? 2 3 and then coming back to 2, it will be like G2 multiplied by G7. So if you apply that logic, we can find out the gains for the corresponding loops, like L1 will be G2 into G3 into G5, L2 will be G2 into G7, L3 will be G6, because it is a self loop of gain exactly equals to G6, then L4 G2 G8 G9, and last one will be G2 G3 G4 and G9. So these points you have to note down. First you have to calculate the gain of corresponding individual loops, and then we need to identify that pair of touching loop, pair of non-touching loop, and so on. And then based on that, we need to calculate the value of delta. That's it. And once you know the value of delta, delta 1, delta 2, then the things are very simple. We need to club them, put them into one specific formula, apply logic of Mason's gain formula to calculate the value of transfer function. So in step number 4, calculations for system determinant. So in this case, first of all, we need to identify that how many number of uh, pair of touching loops or non-touching loops are there. So in this numerical, we have identified that we are having two pairs of non-touching loop. And what are they? First one is L2, L3, and second one is L3, L4. So L2, L3. Now see here, what is L2? So L2 is formed between 2, 3, 2, and L3 is formed between 4, 4. So from this, it is very clear that we don't have any common node in between them. So this will be the pair of non-touching loop. In the same way, L3 and L4. See, L3 is formed between 4, 4, and L4 is formed between 2, 3, 5, and then coming back to 2. See, let me show these over here. This will be your second, this will be a third. So these two are a pair of non-touching loop. In the same way, L3 and L4. So this will be the loop number 3, and loop number 4 is formed like this. Started with this, then this, and then coming back to this. So this will be our loop number 4. So from this, it is very clear that 2, 3 are a pair of non-touching loop. In the same way, 4, 3 are again the pair of non-touching loop. The same thing is mentioned over here. Gain product of first non-touching loop pair will be what we need to do. We need to take care of gain product. So L2 gain we have already calculated, L3 gain we have already calculated. The thing is that we need to multiply them, L2 into L3. That's it. So what will be the gain for L2? The gain for L2 is nothing but your G2 multiplied by G7. And what will the gain for third loop? It is simply G6. So we need to multiply L2 into L3. That means G2, G6, G7, or G2, G7 into G6. In the same way, the gain product for second non-touching loop, it will be the product of L3 into L4. So L3 will be your G6, and what is L4? L4 is G2, G8, G9. G2, G8, G9. That's it. So we need to multiply them. So it will be like G6 multiplied by G2, G8, G9. So these are very important in order to calculate the value of delta. Apart from this, pair of three non-touching loop in this case is going to be 0. That means इस particular structure में 3 pair of non-touching loop है ही नहीं. 2 pair of non-touching loop है, and that two दो ही है. एक second and third और एक है third and fourth. Once we identify all the possibilities, then we need to use this formula to calculate the value of what? Delta. So delta is going to be 1 minus summation of all individual loops. So here we need to take L1 plus L2 plus L3 plus L4 plus L5, and then plus summation of gain product of all possible two non-touching loops. So here we have only two possible pair. First one is L2 L3, and then second one will be L3 L4, and then summation of gain product of all three non-touching loop, this will be 0. So if you apply that logic, you will get this equation as an output. So equation number 4 indicate the expression for system determinant. System determinant. That is very important. So I want everyone to please note down this equation. Equation number 4 indicate the expression for system dependent determinant for this particular case. So delta is 1 minus g2 g3 g5 plus g2 g7 plus g6 plus g2 g8 g9 plus G2, G3, G4, G9, and then in the last we have G2, G7, G6 plus G2, G6, G8, G9. So that will be your equation number 4. I hope everyone done with this equation. Then we need to find out, is there any possibility to have the loops, maybe individual loop, maybe a pair of two non-touching loop or three non-touching loop corresponding to the concept that they are not in touch with your first forward path. I think there will be no such loop available in the circuit, because the first forward path is exactly the straight line like this, and all the loops which are available in the structure are going to touch at any one of the node, maybe at node 2 or node 3 or node 4 or node 5 to that particular forward path. So the value of delta 1 is going to be equals to what? 1, because 1 minus entire term is going to be 0, so it is going to be 1. The same thing is mentioned over here. See, delta 1 is going to be 1. But with respect to second forward path, I think there will be a possibility to have a pair of individual loops which are not in touch with your second forward path. Now see, second forward path is like this, up to 3, no doubt. And then from 3 to 5, we are following this particular path. 3 to 5 like this path. And then from 5 to 6 we are moving like this. So this will be the loop, or you can self loop, which is not in touch with your second forward path. Because if you see second forward path, it is formed in between node 1, then node 2, then node 3, and then node number 5 and node number 6. This will be the nodes which are responsible for the formation of what? Second forward path. But if you see loop number 3, which is your self loop, that is formed at node number 4. So from this, it is very clear that this node is not in common with your second forward path. So we can take this loop gain G6 to calculate the value of what? Delta 2. So in that case, the expression for delta 2 will be like delta 2 is going to be 1 minus loop gain of individual loops. So here we need to take G6 and then plus loop gain of, yeah, summation of product of loop gain of two non-touching loop. This will be 0, because we have only one loop that is not in touch with your second forward path. Because 1, there will be no pair of loop gain, hence it is going to be 0. So delta 2 is going to be like 1 minus G6. That is important. So the same logic is applicable over here, and the value of delta 2 is going to be 1 minus G6. I hope this point is clear to everyone, how we have calculated the value of delta 1 and delta 2. In the previous numerical, the value of delta 1 and delta 2 both are nothing but 1 in previous example. But in this case, delta 1 is 1, but delta 2 is not exactly 1. It has some value. That means there are some loop available in the structure which are not in contact with your second forward path. That is important. So once we have done with this, now it is very easy for us to apply Mason's gain formula to calculate overall transfer function. So this will be the answer for the numerical. Like C of S by R of S is going to be equal to uh, P1. So this will be the P1 multiplied by delta 1, which is 1. Then P2 multiplied by delta 2, which is 1 minus G6 whole divided by delta. And if you simplify this, you will get this final answer. So this is what the process to apply Mason's gain formula to find out the transfer function for a system if its signal flow graph is known to us. So I want everyone to please write down this. This will be the final answer. C of S by R of S is going to be like this. So in the gate, it may not be possible that you may have such type of huge structure to find out the value of transfer function using Mason's gain formula. But the thing is that it may possible that you have a structure and they may ask any one of the point from step number 1 to step number 4. For example, structure is given to you and you're supposed to find out that how many number of forward paths are there. That means you need to find out the value of n, कि n कितना रहेगा. या ऐसा भी हो सकता है कि स्ट्रक्चर आपको गिवन रहेगा और पूछा जाएगा कि लूप्स कितने हैं. दैट मीन्स यू नीड टू फाइंड आउट द नंबर ऑफ लूप्स कितने रहेंगे. या इट मे पॉसिबल दैट दे मे आस्क यू that how many number of pair of two non-touching loops are there or three non-touching loops are there. So a kind of intermediate steps may be asked in gate for say 1 mark or say 2 mark, but the thing is that you should know, or in some cases it may found that some kind of very simple structure but logical structure is given to you, and your objective is to find the value of transfer function using Mason's gain formula, but the structure is quite simple. So the thing is that you should know what exactly Mason's gain formula is and how that formula is applicable to find out the transfer function for the system. That is important. So if you have done with this, let us move to the next numerical on the topic Mason's gain formula. Okay, so determine the overall transfer function system represented by the following block diagram using Mason's gain formula. Now, in this case, we have represented the system in some different form. This is nothing but your block diagram representation. So here, the system is represented in the form of block diagram. And now our objective is to find its transfer function using Mason's gain formula. What will be the transfer function? Now, I told you that Mason's gain formula is applicable for signal flow graph, but here the system is represented in the form of block diagram. So what we need to do? First of all, we are going to convert this block diagram into its corresponding signal flow graph. And then in the next step, apply the logic, that means from step number 1 to step number 4, to convert this signal flow graph into its corresponding transfer function using the concept of Mason's gain formula. So this will be the logic to solve this particular numerical. Here we have block diagram representation for the system, convert that into its corresponding signal flow graph, and then apply the logic of Mason's gain formula to find out its transfer function. That's it. So this portion is known to us. That means if you know the signal flow graph, how to apply Mason's gain formula to calculate its corresponding transfer function. But we don't know if we have block diagram representation, how to convert it into its corresponding signal flow graph. That is important. Again, it is very simple. The thing is that to convert block diagram into its corresponding signal flow graph, first of all, in block diagram we need to identify that how many number of summing point and takeoff points are available, and then we need to assign each summing point and each takeoff point by a separate node. That is important. Separate node. And then we need to maintain the flow of signal in the signal flow graph in the same way they are mentioned in the corresponding block diagram. So this is the very simple topology that we need to implement in order to convert block diagram into corresponding signal flow graph. So here we have total I think two summing point. First one is S1, second one is S2, and two takeoff point. One will be available at T1 and another one will be available at T2. So S1, T1, T2, S2 are the summing point and the takeoff points available in this block diagram. So what we need to do, we need to indicate these summing points and takeoff points by a separate node. For example, let me indicate them over here. So let us consider that this will be the node for summing point. Then this will be the node for first takeoff point, then this will be the node for second takeoff point, and this will be the node for the second summing point. And then corresponding to that, the reference input signal and the controlled output signals are also indicated by some reference input node. So here we need to take this as r of s, or you can take that any value, it may be 1 or it may be 2, and here we need to take that value. So here we need to take this as r of s, and this is going to be your c of s, and then we need to club them. For example, in between summing point and takeoff point, we don't have any, what we can say, signal. Actually there is a signal, but we don't know what exactly the signal is. So how we are going to represent them? So we need to club these two by providing the signal flow of gain exactly equals to 1. And then from node number t1 to node number t2, we have a branch of gain exactly equals to g1. So it will be like a branch of gain exactly equals to g1. In the same way, if you see 2 t2 and s2, again we are having a branch of gain exactly equals to 1. And then from s2 to c of s, again we have a gain of 1. And then from t1 to see from t1 to s2, we have a branch of gain exactly equals to g2. So from t1 to s2, we have a branch of gain exactly equals to g2. In the same way, from t2 to s1, we have a gain of branch exactly equals to h1. So from t2, this is your t2. So t2 to s1, we have a branch of gain exactly equals to what, h1. And then from this r of s connected to c of s with a branch of gain exactly equals to 1. So this is what the logic that we need to implement to convert the block diagram into its corresponding signal flow graph. And once we have this, now it is very easy for us to find out Mason's gain formula, or to find out transfer function using Mason's gain formula. The same logic is applied over here, that whatever the number of summing points or takeoff points, each we are indicated by a separate node. So here this indicate first summing point, this indicates second summing point, this indicate first node, this indicates second node or first and second takeoff point, and then we need to club them. This indicate your reference input indicated by some separate node, this indicate your control output indicated by some separate node over here, and then based on the signal that are connected, or based on the block that are connected in the block diagram, we replace them by a branch with gain exactly equals to the gain of the block maintained between those 2 points. So this is how we can convert the block diagram into its corresponding signal flow graph. That's it. So I want everybody to please draw this. First you have to draw this. This is the given numerical in which the system is represented in the form of block diagram, and then we apply that logic, represent each summing point, each takeoff point by a separate node, followed by reference input by a node, control output by a node, and then apply that logic to convert that from block diagram to signal flow graph. So if you have done with this, then this will be the final signal flow graph representation. And if you have done with this, then it is very easy for us to find out its transfer function using Mason's gain formula. Now what we need to do, we need to find out how many number of forward paths are there. So I think in this case we have two forward path. First one will be like straight forward path, see, like this. R of S, S1, T1, T2, S2, and then reaching to C of S like this. And the second forward path is like R of S, S1, T1, and then move to S2, and then like this. So in this case, we have total two forward path, and hence the value of n is going to be equals to 2. So what will the gain for first forward path? It will be like 1 into 1 into g1 into 1 into 1. So it is going to be like g1. In the same way, gain for second forward path is 1 into 1 into g2 into 1. So this will be g2. This will be the gain for second forward path, g1, g2. I hope this is clear to everyone. Now it is quite repetitive session. Then apply Mason's gain formula to convert that into the transfer function. So in step number 1, we need to identify number of forward paths and reduce the formula into specific one, p1, p2, delta 1, delta 2, delta, and then reduce that particular formula to this equation. This will be the equation number 1, p1 into delta 1 plus p2 into delta 2 divided by delta. And then calculate the forward path gain. We have already calculated this. So just note down this. P1 is going to be G1, P2 is going to be G2. Let this will be equation number 2 and this will be equation number 3. And then we need to identify that loop gains. That is important. So I think in this case we have only one loop. Let us check. So calculations for loop gain. So in this case we have only one loop. And what is that loop? The loop is like this. Started with node number S1, then T1, then T2, and then coming back to again S1. So this will be the loop like this. This will be the first loop. So if the loop is formed between node S1, then T1, then T2, and then coming back to again S1. And what will be the gain for this loop? It is simply the gain of branches which are responsible for the formation of that loop. So it is going to be like 1 into G1 into minus of H1. This is important. So this is going to be like minus G1 into H1. This is very important. So same logic is applicable over here, and the loop gain for first loop, or that is the only loop available in the structure, L1, which is nothing but minus G1 into H1. Then it is very simple to find out the system determinant, delta. In the given signal flow graph, there is only one individual loop, and hence the pair of non-touching loops are going to be 0. That's it. So delta is going to be like 1 minus summation of individual loop, and here we have only one loop. So delta equals to 1 minus L1. L1 is minus of G1 into H1. So this minus minus will be a plus, because here L1 is minus G1 into H1, and in the formula again we have minus. So this minus minus will be plus. That's why here we have plus sign over here. So delta is going to be 1 plus G1 into H1. Remaining portion is 0. Because the remaining portion is 0, that's why delta 1, delta 2 are going to be 1. Because we have only one loop in the structure. Now we can find out the overall transfer function of the system. Apply Mason's gain formula, P1 delta 1 plus P2 delta 2 divided by delta. Put the value of P1, P2, delta 1, delta 2, delta over here. You can get this as the final answer. Because delta 1, delta 2 are nothing but 1. P1, P2 are nothing but G1, G2. And delta is 1 plus G1 into H1. So this will be your final answer. I hope this is clear to everyone. how we can apply the logic to convert block diagram into corresponding signal flow graph, and then how to apply Mason's gain formula to find out its corresponding transfer function. Now let me give you one homework, or you can take more than one. This will be the homework for you. Determine the overall transfer function of the system represented by the following signal flow graph using Mason's gain formula. The system is known to us, that twin signal flow graph, and your objective is to find out how many number of forward paths are there, how many number of loops are there, and then you need to find out its corresponding transfer function using Mason's gain formula. The thing is that you need to apply proper logic. Let me give you the answers for this, but you have to try at your home, and please check whether you are getting these values or not. So P1, P2, that means here we have two forward paths of gain indicated by symbol P1, P2. Now in this case we have two loops indicated by symbol L1, L2, and their gains are minus G1, H1 and minus G4, H2. And then the value for delta is like this: 1 plus G1, H1, G4, H2, G1 into G4, H1 into H2. Then delta 1 and delta 2 are like 1 and 1 plus G4 into H2. So all these values are known to you, like P1, P2, L1, L2, delta, delta 1, delta 2. The thing is that club them, put them into one formula, that is Mason's gain formula, to find out its transfer function. So check this value, whether you are getting these values or not. Take this as an homework. So finally, if you club them, you will get this as the final answer. Transfer function is going to be like this. And then another numerical as an homework. Again, in this case, our objective is to determine the overall transfer function of the system represented by the following signal flow graph using Mason's gain formula. So the structure is something like this. And our objective is to again find its corresponding transfer function using Mason's gain formula, or MGF. Again, I will give you the final answers. In this case, we have only one forward path, then four individual loops L1, L2, L3, L4. Then pair of two non-tangent loops are like this. Now this is quite tedious process. You need to identify very carefully that how many number of loops are there, and out of those loops what will be the possible combination of pair of two non-touching loop, three non-touching loop. That is important. So in this case we have four loop and four pair of two non-touching loop. That is important. The thing is that you need to observe very carefully. You will get these answers. And once you have done with this, apply the logic to find delta, delta 1, delta 2, and then apply the formula. In this case we have only delta 1 because we have only one forward path. So the transfer function will be like P1 delta 1 by delta. So P1 is known to you, delta 1 is known to you, delta is known to you. Apply and find out the transfer function for that particular system. These are some homeworks that I'm going to give you as an assignment. You need to solve these. It will provide you confidence on this particular topic. And once you have done with all these type of numerical, then it is very easy to solve any numerical if they are asked in GATE based on this particular topic. Again, another numerical, you may take this as an homework. Determine the overall transfer functional system represented by the following sets of equation. Now instead of providing the representation of the system directly in the form of signal flow graph, now in this case we have the representation of the system in mathematical modeling. And we have done this type of questions in the previous case. If you know the mathematical modeling of the system, how to find out or how to draw its signal flow graph. So apply that same logic in this case to first convert this mathematical modeling of the system into signal flow graph. And once you know signal flow graph, apply the logic of Mason's gain formula to find out its transfer function. So This is what the hint to solve this particular numerical. Now here, first identify that how many number of nodes are there. See, x1, x2, then x3, x4, x5. So here we have total 5 nodes. First we need to name them, like this will be your x1, here we need to have x2, here x3, this will be x4, and then this will be your x5. And then we need to take one by one equations to indicate the flow of signal between the remaining nodes. For example, if you take from first sub equation, like x2 is equals to a times x1 plus f times x2. So x2 is equals to a times x1. So there will be a signal of gain exactly equals to a, which is coming from node x1 towards node x2. So x1 to x2 with a gain of branch a. And then we have one more signal coming from x2 towards x2 with a gain of f. So this will be your self loop, like this. In the same way, apply the same logic for the remaining equations, like x3 is nothing but b times of x2. So x3 is nothing but b times of x2. And then we have x4, x3 is nothing but e times of x4. That means there is a signal which is coming from x4 towards x3 with a gain of e. So x4 towards x3 with a gain of e. That's it. In the same way, if you apply the logic to this equation, it will be like one signal coming from x3 towards x4 with a gain of c. See, one signal is coming from x3 toward x4 with a gain of c. And then x5 to x4 with a gain of h. x5 to x4 with a gain of h. In the same way, if you apply the logic to this equation, it will be like x4 to x5 with a gain of d. So x4 to x5 with a gain of d. And then from x2 to x5 with a gain of h. x2 to x5 with a gain of, I think, g. It's not h, it's g. So you apply this logic, you will convert this mathematical modeling into its corresponding signal flow graph. I hope this point is clear to everyone. How we have converted this mathematical modeling into its corresponding signal flow graph. Then it's very easy for us to apply Mason's gain formula to calculate its transfer function. This is what the tricky portion of this particular numerical. Draw this diagram, it is very important. If you know this, then it is very easy to find out number of forward paths like P1, P2 in this case, ABCD and AG. And then individual loops. Here we have 3 loops, L1, L2 and L3. Then apply to find out pair of non-touching loops. So in this case, we have 2 pair of non-touching loops. Then find out the value of delta, then delta 1, delta 2, and then apply Mason's gain formula to find out the overall transfer function. This indicate your final answer in this case. So transfer function for this case is going to be like this. So in this way, we are completed the portion of signal flow graph, what exactly signal flow graph is and how signal flow graph is important to find out the study of the system. The thing is that if you know signal flow graph, apply Mason's gain formula to find out its transfer function. In some cases, it may possible that we have the representation of system in the form of block diagram. Convert that into signal flow graph, then apply Mason's gain formula to find out its corresponding transfer function. In some cases, it may possible that we have mathematical modeling of the system. Convert that into signal flow graph, and then apply Mason's gain formula to find out its corresponding transfer function. In the next lecture, we will start another important topic of control system that deals with block diagram. What is block diagram? How to draw block diagram for a system, then how to apply various rules of block diagram reduction technique to convert that into its corresponding transfer function. Thank you.